day 2. I'm going to split this one in 2 pieces as well. I'm not sure how long those videos are going to be, so I want to make sure that we have, you're not getting bombarded too much with video on this one. So you're going to identify how transformations change parent function graphs. So we're going to just start with a simple function, say absolute value of x. Absolute value of x is a nice little V-shaped function with a slope of 1, and I guess I should use lines, probably come out better. So absolute value of x, and again, absolute value of x has a nice linear slope of 1 on the right and a slope of -1 on the left. But what we want to see is what happens if I start moving things around. A slide is a transformation. It's just the shape doesn't change. It moves to the left or moves to the right, moves up, moves down. I can do that. I can do both. There. Notice still got a slope of 1, still has a slope of 1, but we can see that the vertex moved from the 0. A shrink would be that it's shrinking, so maybe getting closer to the y-axis, a vertical shrink. You get a slope maybe of 2 or 3. And on this side would be -3, so you can see that the V-shaped is much smaller. A stretch is maybe you have a slope of 1/3 or -1/3, so a little bit bigger. And a reflection is just going to be your original one reflected over the x-axis. Now these are all of the different types that we're going to be looking at so that you can see what's going on. Okay, so the first one we're going to look at is a vertical translation, or what they consider to be a slide. So you have y equals f of x is your original function, then y equals f of x plus b is the function shifted up that many units, b units. Okay, excuse that interruption. I tried to get that pause button as quickly as I could. Now, if f of x is your original function and y equals f of x minus b is the function, then you're going to just simply shift it down. So we're going to look at the square root of x. So square root of x, I can do a table. We can do a little itty bitty table, but we can go through and identify. If I put 0 here, I get 0. Okay, let's try them again. So if we have 0, our x value is 0. Try to make sure you guys can see that point there. And if I'm going to just, because this is a square root, I'm only going to use perfect squares. So 1 is a perfect square. Square root of 1 is 1. And then next perfect square is 4. 1, 2, 3, 4. Square root of 4 is 2. And we can see our nice little shape moving on here. And we graph this thing, and we get something that looks like this. Now, I am going to use and abuse these points here by grouping them together. And then I'm going to clone it. So now I've got this graph here. You can see it's exactly the same. But when I move this over here, this time they go move it up 2. So I'm going to take this entire graph and we move it up 2. There it is. Notice here it says 0 plus 2. We went up 2. 1 was at 1, moved up 2. This one was at 2, moved up 2. Now I can do this again for the next one and clone it. And this time they want us to go down 3. So I take this one and it's 1, 2, 3. Yes, I am looking at my my 0 point as I was doing that. And so you can see that all of them have the exact same shape. Only difference is that this one was moved up 2, this one was moved down 3. Now, notice that your f of x is the plus 2 and minus 3 is outside of the function. It's not included in with the x. And that is a big thing to pay attention to. Okay, next one would be a horizontal slide. A horizontal slide, notice this time it's going to be inside the parentheses. Original f of x, now we have f of x plus d. Same as with our trig function, inside that parentheses, it started moving it left and right. always go with the opposite sign. A plus is going to move it to the left. A minus is going to move it to the right. Because what we're looking at, and this is something that we could talk about more too, is you get y equals some a value times x minus h to some power. Let's use n plus k. That k value is moving it up and down. This h value is going to move it left and right. They're using d, probably because the book uses d. But I want to point out it's a horizontal movement, and it's opposite because it's x minus. The formula says x minus. So this guy here moves to the left because it's x minus a negative d. There's your movement. Okay, so let's look at some of these. So we're going to play with x cubed. X cubed is if x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 8, which is going to go off our 4 here. And go the other way. If x is negative 1, we get negative 1, because 1 cubed is 1, negative 1 cubed is negative 1. If I go to negative 2, it jumps down to negative 8. I'm going to do my best I can to draw this curve, but you guys all know how it works on here. So it comes down, looks quite linear this way, and then keeps on coming down. Okay, not the most perfect curve, but we're going to use it the best we can. So I'm going to group these points together and then clone it. That way I can show you this movement idea here. This one, this is where it usually was, and they want me to move it to 3. So, but it's plus 3, so I'm going to move it this opposite direction. I use this button right here to point. I know it started at 0, so I went over 3. Now, how do I know I did this correctly? Well, here we go. Look at this value here is negative 2. 3 minus 2 is 1, and 1 cubed is 1. So I know I put this in the right spot. Besides, how else am I going to keep my y value of 0 than to move it to negative 3? Negative 3 plus 3, 0. Okay, so let's try this one more time. Clone it again. And this time they want us to move it to the right too. So using my point right here, 1, 2. Again, 2 minus 2 is 0. That's how I'm able to keep my y value to be 0. But I can also look at what if I plugged in 0.3. 3 minus 2 would be 1, and 1 cubed is 1. So this is a shortcut. I'm going to throw this out there. If you have trouble graphing these things because you don't like going, oh, this is plus and this is what, you can always make a table of values and just graph it from there. But the biggest thing is identifying that vertex. This would be considered the vertex of where it went to. So that way you know what y values to choose, especially if you get something with a fraction. Okay, let's try the next one, a flip. This one you're not going to get really good visual on it, but we're going to try the best we can. If f of x is your original function, if it's outside, it's going to reflect over the x-axis. So you take the whole f of x, throw a negative sign in front, it's going to flip it over the x-axis. But if you put it with the x, it's going to flip it over the y-axis because it changes the x values. Inside changes x values, outside changes y values. So there's our absolute value again. So let me use my lines to get it going. So make sure I got a nice slope of 1 going both directions. Group these two together. And then clone it. So if I got the negative on the outside, this thing gets flipped. And I just have to bring it down to where he's supposed to be. He got flipped. Now if I clone this guy again and bring him over here, there's where he's at. But I want the flip over the y values. So I flip it again, this time left and right. Okay, it shifted over, but it's supposed to, there, it got flipped over left and right. But notice nothing else, I can use the fact that this line was longer to begin with, and now he's over here. And so, again, if you want to test your values, keep in mind absolute value is always positive. So anything I put inside is going to give me a positive number. That negative sign on the outside made all of these values negative. But this guy, I throw a negative inside, didn't affect it at all because he's already negative. You know, it doesn't, or he's always going to be positive. -3 is 3. 3 is 3. It doesn't matter. But I at least could show you that that's what was happening there. Okay, vertical stretch or shrink. Here we get a little bit more difficult, I guess you can say. If y equals f of x is your original function, then a times f of x is a function that will stretch or shrink vertically. Notice here, stretching vertically if absolute value of a is greater than 1. So anyways, this guy is not a, can be a fraction, but he has to be a fraction larger than 1. Shrinking vertically, the absolute value of a is between 0 and 1. So it's always a fraction. But it's a fraction smaller than 1. So we're going to look at this and see what we have going on. X squared, if I put in 0, I get 0. 1 squared is 1. 2 squared is 4. And then this guy has a nice little line of symmetry. So you can just use your line of symmetry to come to the other side. 1, 2, 1, 2. I also want to point out to you that it has a nice little 1, 3, 5 pattern. That's because he's x squared. That from 0, you go over 1, up 1, over 1, up 3, and then over 1, up 5. I can't go 5. Okay, again, let's see if I can use one of my tools to get my, doesn't look like any of these are going to give me a parabola. Here we go. I'm going to go try for that parabola. Well, best I can do. All right, so let's grab all these guys together. And then if I clone him, I can't really clone him, but I can show you guys what was going on. Here's what I had originally. And let me grab a different color. Let's go with green. 2 times x squared. So now I can take that 1, 3, 5 pattern and multiply it by 2. So now it is 2, 6, 10. So still starting at 0. I'm going to do x's this time. Sorry, 0. Now the next one's 2. So over 1, up 2. Over 1, up 2. And then from here, over 1, up 6. 1, 2, 3, 4. Okay, we're way up here somewhere. And this guy again, over 1, up 6. Again, way up here somewhere. And if you drew this in, it's not a huge shrink, but you can definitely see that it's a little bit tighter inside and a little bit tighter, definitely inside the original function. That's what they call a vertical shrink. I'm sorry, a vertical stretch, because you're stretching it towards the y-axis. Okay, now let's clone this guy again. I do realize that, you know, unfortunately you guys get to graph all of those. You know, so, but you get to pause. Clone this guy again, I'm gonna bring him over. And this time, I'm going to do 1/2 times my 1, 3, 5 pattern. But unfortunately, all I get this time is 1/2, 3 halves, 5 halves. So I'm still going over 1, but now I'm at 1/2. Go over again. Now I can go up 3 halves. 1, 2, 3 halves. And then go over 1 and then up 5 halves. 2, 4, 5 halves. This time you can see that I'm outside of the original function. And what happens on this one is that it now has a vertical shrink. It's kind of like pressing down on something. Okay, let me finish this side here up. Over 1, up 1.5, over 1, then up 5 halves. And then you can see that these dots are much further outside of the original graph. Like I didn't put my blue one where he belonged. But there's where you have what's going on with those. Now this 135 pattern is kind of nice, and this is just a pattern for square root or for squares. It works every time. 1, 3, 5, 7, 9, it keeps going. Okay. But this here you go, your vertical stretch. It's kind of like, you know, pulling your arms up above your head, kind of stretches your body, and bringing them down will kind of relax it and bring it down. There's your vertical shrink and stretch. The last one we have is a horizontal shrink and stretch, and we're using x squared again. This time, there it is, the C values on the inside. But notice if it's going to be a horizontal shrink if the absolute value of C is greater than 1. So anything larger than 1. And it's going to be a horizontal stretch if C is between 0 and 1. These two are very, very difficult to tell the difference between the horizontal shrink and the horizontal shrink and a vertical stretch. They almost look very similar, actually. So let's start with our x squared again. Let me go back to my blue pen, so I'm kind of being consistent. So 0, 1 over 1 up 3, which probably puts me to 4. This side up here. This side up here. Again, I wish I can get a parabola going on here that looks really, really good. We're just going to do the best we can with what we got. It was so good until I got right here. Okay. I put all of these points together. And I'm going to clone him and bring him over here. Somehow they ungrouped. Okay, there you have it. Let me go to my green pen. And we can see, oh, now we have 2 times, but this time we're going to square whatever we put in. So if I put in 1, I have 2 times 1, which is 2, squared, which is 4. So over 1, 2, 3, 4. And then I can do the same thing to this side. Remember, this guy didn't change, 0, 0. What if I put in 2? Okay, I'm not going to be able to do a whole lot more. Actually, because if I put in 2, now you have 2 times 2, which is 4, but I have to square them. That gives us 16. You can see that the stretch is going to happen much, or a horizontal shrink is going to happen much quicker. Now, what they mean by this, even though it looks like a vertical stretch, what they mean by this one here is that you're getting your x values are getting closer, and which is forcing your y values up. So it's one of those, to get my y value to be 1, my x value would have to be very, very small. And then the same with this one. I'm going to use even numbers so I have nice perfect numbers. But let me first grab this guy. And go back to my green pen. Now, 1/2 times 0 is still 0. There you go. But 1/2 times 2 gives me 1, and 1 squared is still 1. So, but this time I went 2 and then 1. 2 and then 1. If I put in 4, half of 4 equals 2 squared equals 4. So I go out to 4, and then I'm only up at 2. Okay, and you can see what looks like a vertical stretch is in reality a horizontal, let's say, vertical shrink, a vertical shrink, which in reality looks like a, let me try that again, horizontal stretch that looks like a vertical shrink. That is what I was trying to say. But you can see that that's what's going on. Again, very difficult to tell the difference between these. This guy to a vertical stretch, or this guy to a horizontal to vertical shrink. Unless you have the equations. The equations are going to give it away because you're going to have a number with your x, being multiplied with your x, and then something's being done to it after that. Okay, well, I'm glad I decided to stop here because this is already a 20-minute video. So get this out to you guys, and I'm sure you'll have questions.